Hello, Physics 2 people. Um, so today in this video, I want to talk about Faraday's law of magnetic induction. So first off, let's define induction. An induced effect is a secondary effect of one thing on another. So induced effects sort of are communicated effects or secondary effects. So they're a little different than what we've been talking about so far, where we had a current and it just directly caused a magnetic field, or we had an electric charge which directly caused an electric field. This is a little different. So I'll start by stating Faraday's law in EMF form. Which I believe is actually how it was first discovered. And it says that the induced EMF around a closed loop is equal to the negative rate of change of the magnetic flux through the loop. Okay, well, what the hell does that mean? Let's kind of draw a picture of what's happening here. So we imagine we have some sort of a loop. It could be arbitrarily shaped. It does not matter. And I'm going to imagine that initially there is some magnetic field threading through that loop. So I'll change colors there for magnetic fields. So we'll imagine that we have some magnetic field which goes in and pierces through that loop. So you have magnetic field in red there. Okay. Now, this is kind of the initial magnetic field, and we're just going to take this to be there from start to finish. So if we go back and we reread this, it says the induced EMF around a closed loop is equal to the negative rate of change of magnetic flux through the loop. Well, let's go forward. So first off, what is magnetic flux? Oops. You just go back to black here. So magnetic flux is the integral over the area of B dot dA. And this is just the number of magnetic lines through the surface. Just like electric flux counts electric lines, magnetic flux will count magnetic lines. Now, let's be a little bit more careful here. In this picture, I have a surface S, and it is bounded by a curve C. We'll call the curve, the closed loop, C. And I'm going to kind of sketch in here with, maybe with, let's use blue here. The surface S will be kind of the soap bubble which spans the loop. So hopefully that's kind of clear. So we have this sort of soap bubble surface S, and The magnetic flux would just be the number of field lines which pass through that, and the surface is bounded by C. Now you might be thinking, wait. We had Gauss's law for magnetic fields, which said that, well, we would just say phi, the magnetic flux was zero. How could, so why are we even bothering with this? So remember, Gauss's law for magnetic fields says the magnetic flux is zero, but this is only applies to closed surfaces. And then the zero magnetic flux just says that there's no magnetic charge, no magnetic monopoles. But now we're not talking about closed surfaces, so this doesn't apply. I mean, it's still true, it's just not relevant for us. Okay, so we're going to have open surfaces with a boundary, and we're going to look at the magnetic flux through that surface. Okay, so I'm going to make some space here. I don't want to redraw my picture, so I'm going to erase these equations here. But that's just my comment about Gauss's law and what we've seen so far. So don't get confused. Okay, so Faraday's law, relates an EMF around the closed loop, so that's going to be our loop C, and it equals the negative rate of change of magnetic flux through the loop. So what we're talking about, is if you were to add one more, add a magnetic field line. So for example, you can imagine you brought a magnet nearby, and you were to bring it closer. And remember, this has magnetic field lines, so you'd have, I'm doing those in red, sorry. This has its own magnetic field lines, like this. So if you were to move this magnet closer to this loop, eventually some of these lines would start to pierce through that surface, through that soap bubble. So that would cause there to be an increase in magnetic field lines which cross through that surface. So I'm going to draw in, let's imagine I add a new field line, and I'll just kind of, we'll do that kind of in a darker color. This is my extra magnetic field line, which we are now adding in. So this is a new field line. So we've increased the flux through that closed loop. All right, so what Faraday's law says is if you add a field line, then you create an EMF around the base of that surface, which would be around the closed loop. So adding lines will create an EMF around that loop. So if I kind of redraw my little loop, sorry if it's not exactly the same, then what we find is that the addition, the rate at which we add field lines through the loop gives rise to an EMF which is generated around the loop. And the EMF is generated around the loop. Okay, so I have field lines going through the loop, so when I increase the number of lines through the loop, it gives me an EMF around the loop. All right, and that's the essence of Faraday's law. So in equation form, it is written as the EMF around the loop equals minus the time rate of change of the magnetic flux through the loop. Usually I do flux with capital letters there. All right, so that is the essence of Faraday's law in the EMF form. So some comments here. First off, there's this minus sign. So the minus sign is what's called Lenz's law, L-E-N-Z. And I believe it was discovered first, and so that's the origin of it. I have posted or linked in the playlist a video produced by another institution where they did some demonstrations which kind of show this, where they have a ring on a coil, a solenoid, or next to a solenoid, and then they quickly turn on the electrical current, which causes a lot of field lines to very quickly start to run through this loop, and it generates an EMF in the loop, which actually causes the loop to have its own magnetic field, which causes it to jump and repel the coil. So there's that. The way I think of it is as follows. If I have a loop, and if I add, and let's imagine it was actually made of wire. Because so the issue is, how do you figure out the minus sign? Does the EMF grow clockwise or counterclockwise? That's really what the issue is about. So what I do is I first imagine there's a real physical wire. Okay, and that just helps me to kind of make this more concrete. And so I imagine that I add a field line through that. So I've increased the flux through this loop, this wire. And I imagine now it really is a real wire. And the way that the EMF, the minus sign works in the EMF is such that if you add magnetic flux through the loop, a current is going to flow in this real wire. And the way the current flows is such that the secondary induced magnetic field of this current would actually, so it's going to circulate around the wire and if you notice, the way that it circulates around the wire is such that it's actually trying to cancel out the extra flux that has been added by this field line. So the induced current will cause an induced magnetic field, and the way that induced magnetic field line is oriented is as if it's trying to keep the total flux constant. So it opposes the change. So if we're adding in, so if we add in a magnetic field line here in bright red, it's going to cause a current to flow, and the secondary induced magnetic field actually would orient itself so that it opposes the new line that we've included. So it's kind of funny, and that's how I think of it. So of course, the current in the wire may not be there. Faraday's law applies. It works for any curve, whether or not the wire is actually physically present. But mentally, the way I try to keep track of these minus signs is I imagine there's a real wire and there's a real current, and then that secondary current creates its own magnetic field, which opposes the change. And that's how I try to keep track of the minus signs. Okay, so that's the first observation. And that's the EMF form of Faraday's law. It says that the EMF around any closed curve is, the induced EMF around any closed curve is going to be related to the time rate of change of magnetic flux through that same curve. Okay. Now we're going to come to the electric field form. So we're going to rewrite this. In electric So in the electric field version, we're just going to rewrite the previous one, but interpret it in terms of electric fields. So notice, hopefully you've watched the video describing the difference between electric potential and EMF. When we have, so let's think about this. We have an EMF related to the flux. But what are the sources of EMF that you could possibly have? We've seen batteries. We've all heard of generators, solar cells. But the fact that we have a flux through a loop, that doesn't create a battery or a generator or a solar cell. There has to be some other form of an EMF, which does not require any charge, because again, moving a loop around doesn't create charge. And in fact, what must be true is that in the presence of a time-dependent flux or time-dependent magnetic field, it must be true that we get a new type of electric field. So a new electric field contribution. Okay, so the EMF must be due to, and well, it can't be a charge, it can't be a battery or something, it must be due to an electric field. So therefore, we must have the EMF is equal to the line integral of E dot ds and this is not zero. Remember, in electrostatics, we had that the electric field, and I'll write this as the conservative electric field, was equal to minus the gradient on the electric potential, and this was equivalent to the statement, the integral of E conservative dot ds around any closed loop is zero. Here we have a closed loop and the line integral of the electric field around it must not be zero. Therefore, we must be getting some new contribution to the electric field. we must have a non-conservative electric field. Okay, so in the video on electric potential and EMFs, I described this possibility, and in general, that is what happens. The electric field in general is built out of a conservative portion plus a non-conservative portion. And when we go to talk about energy per charge, this is cast in terms of potentials, or changes in potential, whereas this one is cast in terms of EMFs. Okay, so our new, the electric field version of Faraday's law states that the line integral of the electric field dot ds equals minus, because of Lenz's law, the magnetic flux, right, as a double integral through the surface. So this is through a surface S, and then it's around a closed curve C, and I'll go ahead and label things here. So I have curve C, a surface S, and there's a soap bubble there to show you where S is, and then we have a magnetic field threading that. And what we're seeing is that if you have a time-dependent magnetic field, it gives rise to an electric field which wraps around the boundary. So we must have an electric field which forms loops. I should have said that, so I'll emphasize that in a minute here. So in order for the line integral to not be zero, and we aren't creating charge, so it must be that there must be loop field lines. We've already seen that when you have charges, those give electric field lines which are conservative patterns. But in order to have loops, you need non-conservative things. Or sorry, to have non-conservative things, you have to have loops. So what we get is the following. Basically, kind of the picture is this, that when you have time-dependent field lines which go like this, they're going to give rise to magnetic field lines, which are in general are also time-dependent, which wrap around them. So you have electric field lines, which will wrap around them, and we have magnetic field lines, which run like that. All right, and so that's the field version of Faraday's law. To be honest, this is probably the more fundamental of the two because it's expressed directly in terms of relationships between fields, whereas the EMF version gives you a sense that it has something to do with circuits, and although that's how it was discovered, the field version is really more general, I would say. And I emphasize these new electric fields don't have a direct source in the form of a charge. These field lines can't start, or these electric field lines, they don't start or stop. They form loop patterns. So there is no source per se. They are dynamically generated or induced by the time dependence of the magnetic field. Okay, so that is Faraday's law. In the next video, I'm going to talk about what this implies for the behavior of loops of wire in the presence of magnetic fields and things like that. It'll lead us to something called the relationship between the induced EMF, and then there's also going to be something called a motional EMF, and kind of it's an interesting sort of perspective on things, and it will change the way we view electric and magnetic fields. All right, see you next time.